Hello. In this video, we'll talk about non-separable graphs. We'll give the definition for that. We'll look at a couple examples, and then we'll prove Theorem 3.3, which will tell us that every non-separable graph of order 3 or more, or any graph of order 3 or more, then G is non-separable if and only if every two vertices of G lie on a common cycle. So characterization of non-separable graphs in terms of cycles. So first off, what's a non-separable graph? A non-separable graph, I think I mentioned this in the last video. A non-separable graph is a graph that contains no cut vertices. Now in the last video, we encountered one of these. That was this graph, I believe we called it H3 in the last one. And we just looked at every vertex and we saw the removal of any vertex left a connected graph, and so it was non-separable. Now I want to point something out. I want to just pick a couple vertices of this graph, say this one and this one. And notice that I can find a cycle that contains those two vertices. So how about there to there? Can find a cycle that contains those vertices. So one thing to point out is that every non-separable graph contains cycles. Graph contains cycles. If it doesn't have any cycles, it's not too hard to show that I can remove a vertex of the graph and disconnect it. Say take a longest path in the graph and remove some vertex of it. And since there's no cycles, that'll be disconnected. Contains cycles. And here we saw, I picked those two vertices and I found a cycle between them. But more than that, any two vertices I pick, I can find a cycle that contains both of those vertices. That is, the two vertices lie on a common cycle. So I'll say every two vertices lie on a common cycle. Now this maybe this graph is a special non-separable graph that has this property. What are some other non-separable graphs? In particular, if I want to find, if I think this is true for all non-separable graphs, then, and I want to try and maybe come up with a counterexample, see what could go wrong if I want to try and disprove that, well, I want to think of a graph that has the smallest number of edges and is still non-separable. So if you look at any cycle, Cn, so a cycle of any length, so I have some arbitrary cycle here. This is non-separable. This is sort of one of our minimal non-separable graphs, the smallest number of edges. And if you pick any two vertices, well, clearly they lie on a common cycle, right? They lie on the cycle itself. And so it's true there. So this is an example of a non-separable family of graphs. Right? Each graph in the family is non-separable, is what I mean by that. Other non-separable graphs are, say, complete graphs. That family of graphs is non-separable for k greater than or equal to 2. Any non-trivial complete graph is non-separable. The other thing I want to point out here is so let's look at a separable graph. So remember, paths were separable graphs. So here we'll take a path Pn. This is separable. And I want to point out here we have a vertex of degree 1. And notice that its neighbor is a cut vertex. And in general, this is going to be true. If I look at any graph where I have a vertex of degree 1, so let's say I have, some part of the graph over here, and I have this vertex that's degree 1, well, then this vertex that it's adjacent to will always be a cut vertex. So this is one real quick necessary condition for a graph to be non-separable, is that it can't contain any degree 1 vertices. That is, its minimum degree is at least 2. A graph, if a graph is non-separable, then its minimum degree is at least 2. If a graph G is non-separable, then its minimum degree is at least 2. So we're going to use this fact to help us prove this thing that we're noticing, that every 2 vertices lie on a common cycle. This turns out to be true, and this is Theorem 3.3. So let's go ahead and try and prove this. Let's go ahead and prove the forward direction first. And so we'll assume let G be a non-separable graph. And I'm not going to write it, but of order 3 or more. Be a non-separable graph. So it contains no cut vertices. And what I'd like to show is that every 2 vertices lie on a common cycle. So let's try contradiction on this. Let's assume there are 2 vertices that don't lie on a common cycle and come to some sort of contradiction. So assume that G, so assume to the contrary. That G has, oh no, I want to assume, right, I want to assume that that 2 vertices do not lie on a common cycle. Has 2 vertices, let's say U and V, that do not lie on a common cycle. Actually, I'm not going to name these yet. Let's say G has 2 vertices that do not lie on a common cycle. Because what I want to do here to make things easier for myself, this is going to make the proof run, is I'm going to choose 2 vertices, right? There could be many pairs of vertices that do not lie on a common cycle. I know there's at least 1 pair of vertices. There could be a bunch of other ones. Of all those pairs of vertices, I want to choose a pair such that the distance between them is the smallest out of all pairs. So of all pairs of vertices that do not lie on a common cycle, again, there could be more than 1 pair, choose all pairs, let's say of all pairs U and V. Choose a pair UV such that the distance from U to V is minimum. So I've plucked out a pair such that their distance is the smallest possible of all pairs that do not lie on a common cycle. That means if I find 2 vertices whose distance is less than the distance from U to V, I know they lie on a common cycle. Okay, so I'm going to break this down into cases. I want to first consider the case when U and V are adjacent. So first, suppose that the distance from U to V is equal to 1, i.e. U and V are adjacent. So what does our situation look like? We have U, we have V. They do not lie in a common cycle, and these 2 vertices are adjacent. What I'd like to do is find another path from U to V that doesn't involve this edge, and that'll produce a cycle. So let's see, since G is non-separable, minimum degree is at least 2, as we noted before. So there is some neighbor of U that's not V in particular. So there exists W such that W U is an edge and W is not equal to V. So this is now my situation. All right, that's nice. And I'd like to find a path now from U to V. Of course, if there were no paths from W to V, if there were no paths from W to V, then U would be a cut vertex, right? This is the idea of Theorem 3.2. By Theorem 3.2, since G does not contain any cut vertices, in particular since U is not a cut vertex, by Theorem 3.2 we can say there is a path from W to V that does not contain U. So I have some path now that does not contain U that goes from W to V. And there's my cycle. So this produces a cycle. I'll just say I have the picture there, so I'm just going to say this produces a cycle. A cycle containing U and V. So that's a contradiction, and so U and V lie in a common cycle. So we can assume then that the distance from U to V is equal to some k, which is greater than 1. In particular, UV is not an edge. So I'm gonna find a UV geodesic, a path between U and V of shortest length. So let P be a UV geodesic. And I'll give names to these vertices. Say P is equal to U0, that's U. And then we'll go V1, I'll name the other items V1, V2, Vk minus 1 up through Vk will be my path, my UV geodesic. So this is the shortest path. So what's my situation now? So here I have U, here's V1, and I have this path, here's Vk minus 1, here's Vk. And what I'd like to do again is find a different path from U to Vk, if I could do that, right? If I could find a path from U to Vk that doesn't contain any of these vertices here, then I would have a cycle containing U and Vk, and I would be done. Now, of course, that's going to be hard to do, to find a path between U and Vk that doesn't use any of these vertices. And so we have to be a little bit clever about this. And we're going to have to use a lot of tools. So this actually turns out to be quite a fun proof. I really like this proof a lot, and hopefully you'll see why. So, right, so by assumption, remember U and, so this Vk, right, this Vk is the same as V. I don't think I pointed that out. Vk, this is equal to V. This is my UV geodesic. So notice that the distance from U to Vk minus 1 is less than k. Right, is strictly less than k, less than or equal to k minus 1, which is less than k. I can certainly say that. Otherwise, the distance from U to V would not be, or otherwise this would not be a UV geodesic. So since this is a pair of vertices of distance less than the distance between U and V, so this is distance from U to V, we can say by assumption U and Vk minus 1 lie on a common cycle. Right? Remember, we picked U and V so that of all the pairs that did not lie on a common cycle, that distance was minimum. Here's a pair who has smaller distance than that, and therefore they must lie on a common cycle. So what do we want to call this? Let me double check so I keep this consistent. I think I want to call this C. So let C be a cycle containing U and Vk minus 1. All right, so I'm going to draw a new picture for this. So I have my cycle containing u and vk minus 1. So I'll put u here, and how about vk minus 1 there? And I have some cycle. This is how I would draw a general cycle. Some dot, dot, dots. I'll put some dot, dot, dots over here too. Something like this. So here's my cycle containing u and vk minus 1. Again, by assumption, v, right, u and v do not lie on a common cycle. And so v is not on, let me put some space between these two. Again, by assumption, v is not on the cycle. All right. Where to go from here? Right, so what can I use here? Again, my goal is to produce a cycle containing both u and v, and I'd like to use this cycle. So if I could find a path that goes from v to this cycle, and maybe a path between v and vk minus 1, then I would have a cycle. Actually, wait, yeah, let's point that out. V and vk minus 1, I want to remember here that this is my path p. So vk minus 1 and v are adjacent. And so, yeah, what I'd like to do is find a path from v to somewhere on this cycle, and then I'll have my cycle containing u and v. So how can I guarantee that there's a path from v to somewhere else on this cycle? Well, remember, our assumption is that G is non-separable. In particular, vk minus 1 is not a cut vertex. So since G is non-separable, vk minus 1 is not a cut vertex. Right, this is like the case 1, right? I had two adjacent vertices, and I could, I found this other vertex W, and I knew that there had to be a path between W and V that did not go through U. So, right. That is, there must be some other path besides from V to vk minus 1 back to U. There must be some other path from V to U. So this is Theorem 3.2 again. By Theorem 3.2, there is, right, vk minus 1 can't be the only vertex, right, or sorry, rather, every uv path can't go through vk minus 1. There has to be some other path that goes from u to v. There is a path, let's call it q. There is a, let me be more specific, a uv path q that does not contain vk minus 1. Now, since U is on the cycle, then there's some first vertex, right? So here's my UV path that doesn't encounter VK minus 1. It's possible that it doesn't, right, that this cycle doesn't encounter, or sorry, that this path Q does not encounter the cycle until I get to U, that might be the first vertex on the cycle. So it's possible something like this happens and I go down there. But in that case, right, I'd be able to find a cycle containing U and V. So, right, I'd like to make that a little bit more general. Because U is on the cycle, there's some first vertex of Q that encounters the cycle. So let's say this one. And we're going to call that X. So I'll say since U is on the cycle, there is some first vertex of Q contained in the cycle. Say x. So we're calling that x. And now we have our cycle containing u and v. So, right, to be super clear about this, we'll let yeah, what do I want to say now? Right, we can definitely see the cycle here. So I want to take this part of the cycle and this part of the cycle, and then come back here. That's the cycle that I'm seeing here. So let's see, how exactly do I want to word this? So I'll let right, Q is this path from U to V. So what do I want to say? So let's let this little bit from V to X be called Q prime. So let Q prime be the Vx subpath of Q. So that's this bit here, Vx subpath Q. And then I know, yeah, that I have this Vk minus 1U path on the cycle that does not contain X. So I'll call this P prime. Let P prime be the U Vk minus 1 path on C that does not contain X. So that's this bit here. And then we can say, so then form the cycle, let's call it C prime, by proceeding from, let's say, along, what I called this P prime, by proceeding along P prime, proceeding from U along P prime to Vk minus 1 to Vk or V to V, then proceed along Q prime, that was my Vx subpath, to X, and finally proceed along C from X to back to U. So that's one way I can define a cycle. This cycle C prime is by just telling you exactly how to get from one vertex back to itself along this way. And so this is a contradiction. Since U and V now lie on a common cycle. So no matter what case we were in, U and V lied on a common cycle, and U and V were arbitrary, and so that finishes the forward direction of the proof. So, okay, kind of fun, a little bit messy there at the end to actually describe exactly this thing, but coming up with the cycle, I thought it was pretty fun. So let's handle the backwards direction. So suppose, again, the graph is of order 3 or more, that every 2 vertices lie on a common cycle. And I'd like to show that G is non-separable. So I'll suppose that it is separable. In particular, since every two vertices lie on a common cycle, I know that G is connected. I can say then G is connected. Right, clearly if every two vertices lie on a common cycle, then G has to be connected. And we'll assume to the contrary that G contains a cut vertex. Let's call it V, cut vertex V. So since G contains a cut vertex, we'll use Theorem 3.2 again. By Theorem 3.2, there exists U and W such that every UW path encounters V. So here's my V, my cut vertex. Here's my U. Here's my W. Now, by assumption, U and W lie on a cycle, lie on a common cycle. And so there must be some other path from U to W, right? Something like this. So by assumption, U and W lie on a common cycle. Well, then every UW path does not encounter V. So there is a UW path that avoids V. And so G is non-separable. Or in other words, V is not a cut vertex. Maybe I'll say that. And so V is not a cut vertex. And that concludes the proof. All right. So this is kind of cool. Yeah, if we have a non-separable graph, necessarily every two vertices lie on a common cycle. That'll be useful. Look at that theorem. That was pretty long proof. So thanks for hanging in there with me. So this theorem has a few corollaries that'll also turn out to be useful. One of these is your homework, is a homework problem to prove this corollary. That is, if we start with a non-separable graph and we add a vertex and make it adjacent to two vertices in the graph, then the resultant graph is also non-separable. That's one of them. Yeah, you can read these in the book. I do want to talk a little bit about how this corollary, remember corollaries follow from the theorem. I do want to talk a little bit about how this corollary follows from the theorem. So this one says non-separable, not on-separable, if and only if every two distinct vertices there are two internally disjoint UV paths. So what's an internally disjoint UV path? So here's U, here's V. Internally disjoint just means that other than U and V, the two paths are disjoint from each other. So that means I can find a path like this, and another path that looks like this. So internally disjoint just means besides the end vertices of the path, every other vertex is distinct between the two. And so think about how I can prove that, right? You take U and V. So I'll start with a non-separable graph. So G is non-separable. That means every two vertices lie on a common cycle. Take these arbitrary vertices U and V. They lie on a common cycle. Well, here's my cycle. And that means that I can find two internally disjoint UV paths. And that proves that direction. Going the other way, take two internally disjoint UV paths, like I drew here, and that produces a cycle between U and V. And since U and V can be made to be arbitrary there, we find that U and V lie in a common cycle. So this corollary follows really nicely. This corollary as well follows pretty nicely from the theorem, but I'll let you do that for homework. And that's it for this video. I'll see you next time.